Is Gabriele Sbaiz, and it's about interaction of multiscales for fluids and fast rotation.
Okay, thanks Tobias for the introduction, and thanks the organizer for the invitation. Today we talk about interaction of multiple scale for fluids in a faster rotation regime. Then the main goal is to analyze the mathematical model for fluid on large scale. We can think about the ocean and the atmosphere. If we can try to draw the ocean, we have that the length scale usually is much higher with respect to the height. Then we can modelize our domain here omega like R2 cross 0,1, where R2 stands for the horizontal variable and 0,1 for the vertical one. Then we have an infinite strip. Okay. In the context of fluid on large scale, we have three main characters, three main players that drive and govern the dynamics of the fluid. We have the Coriolis force, the weak compressibility effect, and the stratification effect. The Coriolis force is modelized like a rotation around the vertical axis. Then, here we have x1, x2, and the vertical axis x3. Then we have the rotation around this axis. And then we can write the Coriolis force like E3 cross U, where E3 is for me the unit vector 001, cross stands for the external product by vectors, and the U is the velocity field that depends on the time and the position. Then we have this is equal to minus U2, U1, and 0. Okay. This is a very simplified version of the Coriolis force, but it is well justified at mid-latitude. Then we neglect the variation of the Coriolis force independence of the latitude. From the physical point of view, it is also well known that a strong Coriolis force drives the motion to be planar. That means that the dynamics of the fluid is two-dimensional and take place on horizontal plane that are orthogonal with respect to the vertical axis. Then in this picture, I can write my horizontal plane, and this horizontal plane is orthogonal with respect to the vertical axis x3. Okay, and this is the so-called, so famous Taylor-Pradman theorem, and we will see in the main statement this result also. The second main character is the weak compressibility effect, and indeed we will see this weak compressibility linked to the pressure term, because we will scale the Mach number like a small parameter. The last effect are the stratification effect. That means we have the variation of the density that I call rho, depends on time and the position, and this is due to the gravity. This effect drives the motion to be stratified with respect to the vertical variable. That means that we have the stratification of our fluid with respect to the x3 variable. And then these effects are in fight with the Coriolis force, because for the Coriolis force, we have a planar behavior in two dimensions, and the variable are x1, x2. And here, due to the stratification effect, we have the restoration of the stratification of our fluid with respect to the vertical variable. Okay, now I will present the equation that are called Navier-Stokes Fourier equation. To be precise, the equation are called full Navier-Stokes Fourier equation. We have the continuous equation, that is the equation for the density rho. We have the momentum equation for the velocity field u. Here, you immediately recognize the Coriolis term. Here you have the pressure term, and on the right-hand side, you have the divergence of the viscous stress tensor S. Okay, in a first approximation, you can think about this term like a Laplacian, okay? And then we have two external forces, capital F, that is the centrifugal force, and capital G, that is the gravity. Since we are on large scale, we have this scaling in front of the Coriolis force, that is 1 over Rossby, where Rossby is the dimensional number linked to the importance of the rotation in front of the, okay, and here we have 1 over Rossby to the power 2 because these are the centrifugal effects. Here in front of the pressure term, we have the 1 over Mach number to the power 2, where the Mach number measures the deviation of our fluid from an uncompressible flow. That means more, let's say smaller is the Mach number, more your fluid is incompressible. And the last adimensional number is here in front of the gravitational term, that is the Froude number. And this number measures the importance of the stratification effect. Okay, at this point we have an equation for the density, an equation for the velocity field, but here you have also the temperature. And then we have to recover, we can recover the equation for the temperature from this last row. That's true, this is an equation for the specific entropy S, but you can read this equation like an equation for the temperature. Here Q is the heat flux and sigma is the entropy production rate. Okay, these are my equations. Now I present the scaling that we choose. We take Rossby equal to a small parameter epsilon. We take the Mach number equal to epsilon to the power m, where m is a parameter that is free to vary in all the range greater or equal than 1. And this also, let's say, how do you say? This also explains the title of my talk, because the multiscale are linked to this m. Since m is free to vary for all the range greater or equal than 1, we are able to cover all the possible regimes. And at the end, we choose this scaling that I will call critical, and we will see why this scaling is critical. That is, the Froude number is equal to the square root of Mach. Okay, this is my scaling. I put this ansatz, I plug this ansatz in the equation. Then here we have 1 over epsilon, here 1 over epsilon to the power 2m, here 1 over epsilon to the power 2, here 1 epsilon to the power m. Okay, the aim is to find the dynamics when epsilon goes to 0. That means we would like to describe the limit dynamics for a reduced system that at the limit is usually simple with respect to the primitive system, but still capture the main feature of the original problem. Okay, this is the aim. That means we would like to describe a more simple system in order to have also some information about the original problem. And also we would like to derive the reduced system for the widest range of the parameter m. In particular, we will have two main regimes: the anisotropic scaling, when m is strictly greater than 1, that means that some effects are predominant in the dynamics with respect to the others, or the isotropic scaling, when m is equal to 1, that means all the effects act at the same level. I go back in a previous slide because I would like to say that when epsilon goes to 0, these four guys become singular and drive the dynamics of the motion. Okay, this is the first main result concerning the anisotropic scaling when m is strictly greater than 1. We take our domain, the infinite strip. We take the centrifugal force like the modulus of xh to the power 2. We take g, the gravity, minus 3. And we take or equal m equal greater or equal than 2, or m still greater than 1 and f equal to 0. Moreover, we assume initial data that are small perturbation of constant profile. This is, let's say, the business approximation. And the velocity field is, initial velocity field, sorry, is uniformly bounded. Then we are able to prove that when epsilon goes to 0, the density at the limit is constant. We are able to measure the deviation of the density with respect to the constant profile, same as for the temperature. And also we can describe the velocity field at the limit. That satisfies the Taylor-Pradman theorem here. then it is 0 on the vertical component, depends only on the horizontal variable, and it is a divergence-free vector field. Then we have the conservation of the volumes for the limit system. Moreover, the triplet, the target velocity, the target density R, and the target temperature capital theta solve in the sense of the distribution the Oberbach business system. That is the following one. We have the business balance, that is a balance between the target density and the target temperature with the external forces. Here in this script G, we have the gravity and also the centrifugal force. For the velocity field, we have a Navier-Stokes type equation. And I would like to stress you that this dynamic is purely horizontal, it's a two-dimensional dynamic. And we have for the temperature a transport diffusion type equation. But here we are also able to capture some low stratification at the limit. This because this theta strongly depends on X3. We cannot avoid a dependence on X3 like in the dynamics for the velocity field. And this fact that we are able to capture some low stratification effect at the limit is due to the scaling through the equal square root of Mach. Okay. In the isotropic scaling, that means when m is equal to 1, in the same setting as before, we have the same convergences as before, and the velocity field satisfied the Taylor-Predominant theorem. But now we have to define two new unknowns. Upsilon, that is combination of the target density and the target temperature, and Q, that is combination of target density, target temperature, and also the gravitational effect. Then a priori, since G is equal minus X3, Q depends on X3. But we are able to prove that this is not the case, and Q depends only on the horizontal variables. That means that this spatial combination kills the dependence on X3. And also you can read this Q like a string function for the velocity field at the limit. Moreover, the couple Q upsilon satisfying the weak sense the following equation, that is a quasi-geostrophic type equation for Q. Here again, we have a purely two-dimensional dynamics for Q, and a transport diffusion equation for upsilon. And here again, we have some low stratification effect due to the fact that upsilon depends on H3. Okay. Yes. Okay, this remark, I already talked about that, and I skip. To avoid boundary effect, I have to say that we take completely boundary condition. That means, that our fluid at the boundary is lead. Behind the scaling fluid equals square root of Mach, that means when the fluid number is greater than the square root of Mach, we take the barotropic Navier-Stokes equation, that is the previous system with the constant temperature. Okay, we have set the temperature equal to 1 in the previous system, and here we have put also this variable n, and we would like to understand the interaction between m and n. And we assume the following regime. When m is greater than 1, 2n is greater than m. That means that the fluid number is greater than the square root of Mach, and same as for the case m equal to 1. I will go very fast in this theorem because as the same idea of the previous one, we take initial data that are small perturbation of constant profile. At the limit, we find that the density is constant and the velocity field satisfies the Taylor-Predominant theorem. But in this case, we have that UH is solution, weak solution of the two-dimensional homogeneous incompressible Navier-Stokes system. Then here we cannot see anymore the stratification effect at the limit. Same as for the case m equal to 1. At the limit, we have that the density is constant. We are able to measure the deviation of the density with respect to the static solution. That means that solves the momentum equation when u is equal to 0. Okay. And we have the quasi-geostrophic balance. That means that this deviation is a sort of string function for the velocity field, and this deviation of the density satisfied the quasi-geostrophic equation. Okay, the future perspective are the following: is the multi-scale analysis in the different regimes that are not covered in the previous analysis. Indeed, you have seen that we have a restricted range for n in the case of the barotropic system. And also an open question for the moment is the well-posedness issue for the limit system that arise out for the analysis of the Navier-Stokes problem. Okay, this is my last slide, and we conclude in time, I think. All the results are present in this paper here and in this paper here that will appear in 2023. And then I can stop here, and thank you very much for your attention.
Yeah. We need a bit of detailed study to see why it's different. We don't seem to be getting the same sort of limit equations as conventionally derived, when you really ought to be the same one. It's something to do with the fact that the very strong hydrostatic constraint isn't sort of visible at all in your analysis. Yeah. And I think, but to try and understand why your analysis is coming out different from, let's say, the traditional analysis that leads to quasi-geostrophic and semi-geostrophic scaling, which ought to come out of this, doesn't seem that we need to be getting a different answer. So we need to understand that a bit.
You mean why our analysis is different?
Well, you're not getting the same sort of limit equations.
Why we have the limit equation?
I mean, you should be getting the same thing because you've got.
They are not really the same, because you mean this one, and the previous one.
Yeah, so n equals 1 in the sort of scaling I'm used to will give you a semi-geostrophic.
Exactly. In m equal 1, you have the quasi-geostrophic balance in the both cases, yeah. But here the quantity are different. I mean, yeah. Here you have the deviation with respect to the static solution. Okay, because this rho 1 is this weak limit for this quantity. Okay. In the previous equation, it's a bit different because here we have also the temperature. E is here. We have the density, but also we have the gravitational effect inside. That this Q is not completely the same unknown as before. I mean, plays the same role as rho 1, but it's not the same, of course.
Both your systems only have very limited stratification effects. What you said, one they got hidden altogether, and one it was there, but it was there, but not a very strong influence. While the systems you would that traditionally derived, I will talk about it some other time, will have a much stronger dependence on stratification. So
yes, of course. So
something is different about what you've done.
Yes. This because where is my scaling? Yeah, you can see my scaling. We are in a low stratification regime because if you take fluid, maybe I can write something. It's not so difficult to answer, because if you take fluid over Mach, this goes to 0, right? When epsilon goes to 0. That means that we are in a low stratification regime. For strong stratification regime, from the mathematical point of view, is a very challenging problem. There are only 2 papers, I think. One done by Farisel and Novotny, I don't remember the year, and one by Fanelli, Bocchi, and Fanelli, Prange, and Bocchi, yes. That tackled the problem of strong stratification, because since behind this system you have a wave system, usually you have a fast oscillation in time of the solution, yeah. That you are not able to control this fast oscillation time of solution. And also, if you have the strong stratification, you are not able to pass to the limit on the density and on the velocity field together. I mean,
Yeah, so you mean the convergence of the limit equations is difficult to us.
Yeah, exactly. This is a mathematical, let's say, technical point of view.
I certainly agree with that, because that's fast oscillations means you have to find different methods of proof, and it's very difficult to get a proof. Yeah, I agree with that.
Yeah. Thanks.
So, what the density of a near constant on spectrum in the limit?
Can you speak louder?
In the limit, the density of close to constant.
Yeah.
So, I think in atmosphere, I think we have very strong stratification versus what vertical direction. So, some would propose a linear factor.
Yeah.
And in some cases, there are only linear. So, I think I'd like to see in the limit, density is not good.
Yeah, of course. The point is the same point, let's say, more or less the same point that Professor already pointed out. This is due to the fact that, one, we have a low stratification regime. The second point is that we take initial data that are perturbation of constant profile. This is because if you don't take this assumption, you are not able to close the estimate. I mean, there is only one paper, only one paper done by Fanelli and Gallagher in that is maybe there is also in the references, not sure. No, okay. By Fanelli and Gallagher in 2009, I think, in the Iberian Mathematical Journal, where they treat also the case when the density is not a perturbation of constant profile, but an arbitrary density, initial density. But to pass to the limit, you need more regularity on the initial data, or better, you have to require more regularity that you expect for your data. This because you have some nonlinearities, and if you would like to propagate some regularity, you are not able to do this because you have, for example, the Coriolis force that is a singular term. Okay. The point is, 10 seconds, is to close. Let's say, if you think about in 2 dimension, okay, we have this is minus u2 u1 for me, okay, the velocity pair. If your answer is 1 plus epsilon something, this is 1 epsilon this one plus some term that is linear. Okay, this is, let's say, okay in some sense, and this is has no any more epsilon. Okay, but if you have also here another term, and then you are not able to go on your analysis. I mean, you need something on this term here, on the density here. That's the point.
Okay, so thanks, speaker, again.
Thanks. So this is my phone. Backup.